Okay, so last time we talked about some of the conceptual, I guess, characteristics of how internal flows behave, both from a momentum standpoint and also now from a thermal standpoint. At the end of the day, we have to solve problems involving internal flows, and we will almost always resort to using correlation. So we said that if we're interested in the pressure drop, either the local pressure drop or the total pressure drop in an internal flow, we're going to be looking up correlations for the local friction factor or the average friction factor, right? If we're interested in the heat transfer coefficient, then we'll be looking up correlations for either the local Nusselt number, which gives us the local heat transfer coefficient, or the average Nusselt number, which gives us the average heat transfer coefficient. And we have some idea now how these things behave, how they behave in terms of when the flow becomes fully developed. So today what we need to talk about is just where do you go to get these correlations and what's the functional dependence of them, and also, I guess, why do they behave the way they do is kind of important. Can we bring back the understanding that we have now, hopefully, about internal flows to why the correlations behave as they do. So let's start with the friction factor correlations. So right here we can look at the functional dependence of these correlations. So these correlations, whether we're talking about a local or an average friction factor, they're a function of the Reynolds number, and that Reynolds number is defined based on the hydraulic diameter and the mean velocity. They're a function of, in the case of a local friction factor, x over the hydraulic diameter. So this is basically asking the question, are you in the developing region or are you in the fully developed region? They're a function of how rough the duct wall is. So this E is the roughness size on the duct wall, and is non-dimensionalized by the hydraulic diameter. So this is a relative roughness, right? Typically this is a pretty small number because for most ducts the roughness on the surface is a pretty small fraction of the diameter itself. And they're a function of the duct shape, right? So do you have a round duct? Do you have a square duct? Do you have some kind of an annulus? All these different things affect the friction factor. So that's the functional dependence. And if you go to chapter, depending on what book you're using, chapter 5 or chapter 9, if you go to that chapter about internal flow, you'll see, just basically correlation after correlation after correlation that tells you what's the friction factor. And these correlations are divided up based on what kind of duct shape do you have. Are you in the developing region or the non-developed region? Is your duct smooth, and all that kind of stuff. And a lot of times they're charts or just equations. These have been placed into what I think is a pretty convenient format as procedures in ease. So we should maybe go look at those, and you can understand how to use them. So here's ease. If you go to options and then function information, and then you go down here to the heat transfer library. One of these drop-down menus is convection. All right, so here's convection. If you come down here to the lower panel, then you'll see that you have a few choices here, but the choices include internal flow, external flow, and free convection. So we've already talked about external flow. Right? These are correlations for flow where the boundary layers don't become bounded, so flow over a body, right? We talked about this previously, flow over a sphere or a cylinder or so on and so forth. And you had two choices there, dimensional or non-dimensional, right? If you go up and look at internal flow, you actually have four choices here, right? So you have either non-dimensional, and this top one is non-dimensional average, or down here you have non-dimensional local, right? And of course you have the dimensional equivalent to those. So non-dimensional average, let's start with that. That's going to give you, if I click on this, for different types of ducts. So here, circle, we have a rectangular duct, we have an angular duct. So for all these different types of ducts, this is going to give you the average friction factor and the average Nusselt number, right? So let's talk just about the friction factor now. You can see here that the way that you call these things, because it's a procedure, actually let's just paste this in here and we can look at it a little more carefully. So I'll make it a little bigger if I can. So you can see that it's a procedure, right? So you have a list of inputs here, and then a colon, and then a list of outputs, right? So the inputs include, well, let's go back and look and see what the inputs have to include at least the duct shape, the Reynolds number, the relative roughness, and L over D, right? So the duct shape is based on which of these procedures did we call. When I'm calling the pipe flow procedure, that's a round duct, right? If I called a duct flow procedure, that'd be a rectangular duct. So the pipe flow is basically which of these procedures are we calling. The Reynolds number is the first input argument here. The Prandtl number we don't need, actually. I mean, we have to put something here, but it doesn't matter if we're only interested in the friction factor, because the friction factor is not a function of Prandtl number. The next argument is L over D, so this is the length of the duct divided by the hydraulic diameter. It's how long we are. And then this last argument here is the relative roughness. That's E, the roughness element size, over D, right? So all of the functional dependence that we said the friction factor has is encapsulated in this call right here. And then after the colon, we have two Nusselt numbers, and we'll come back to why we have two Nusselt numbers in a little bit, but then we have a friction factor here, right? So this is the average friction factor. This would tell us something about the total pressure drop. So again, if I don't care about the Nusselt numbers, then whatever I put here for the Prandtl number won't matter. I can't not include this, because of course, you know, that the first input is the Reynolds number, the second input is the Prandtl number, the third input is L over D, and the fourth input is relative roughness. But I can just put anything here, one, it doesn't matter. And if I only care about the friction factor over here, then again, I have to put it in the right order, but I could just leave this blank, comma, and then leave this blank, and it will only now return for me the friction factor. All right, so that hopefully that makes sense. Like, this would be how I would get the average friction factor for a round duct. If we go back up here and look at this again for a second, if you come down here and look at local, they're going to look pretty much exactly the same. It's just that this time now we're going to get the local friction factor instead of the average friction factor. And when we get to Nusselt numbers, we'll find we're getting the local Nusselt numbers instead of the average Nusselt numbers. So all this equation, all this procedure is doing is just programming the best set of correlations that we could find, right? And then based on what you give it here for the inputs, it'll go off and find, you know, do I need turbulent? Do I need laminar? Do I need a developing correlation, and all that kind of stuff, so that you don't have to do that. If you didn't have this, it'd be fine, right? You would just have to do that yourself. Go find the appropriate correlation. All right, so I think one last thing we should do before we move on to the Nusselt number is actually look at how these correlations for friction factor behave. Because, you know, it's one thing to be able to go off and use a correlation and pull out a friction factor and use that friction factor to solve a problem. It's another thing to be able to understand why it is that the friction factor is doing what it's doing, and based on that, then be able to explain trends and characteristics and observations that you make when you take data or you're building a model or something like that. So what I've done here is plot the fully developed friction factor as a function of Reynolds number, okay? And I'm doing this out in the region where L over D is very, very large. So that's what fully developed means, right? So either X over D or L over D, I'm doing it out in a region where that's gone towards infinity. So I'm way out, if you look at this plot, I'm way out here where X doesn't matter anymore, and where the average friction factor and the local friction factor have come together. Right. So in terms of dependence here, you can get rid of this as a dependent, right? This is going to be a function then of only Reynolds number, relative roughness, and duct shape. Okay. If I picked a value off of this chart and used it to solve a problem, I should expect that this value is always going to be lower than the actual friction factor. And the reason is that, why? Because I'm using the value way out here where the friction factor has achieved its lowest value. This entry region here is going to make the actual friction factor somewhat larger than the value I would pick off of this chart, right? How much larger depends on how long your duct is and how important this entry region is. Okay, so we're a function then only of the Reynolds number. So I'm plotting it as a function of Reynolds number. We're a function of relative roughness and duct shape. So I want you to look at the results here. First of all, there's an obvious transition between laminar and turbulent, right? This is around 2800, which we said was right about where I would go from a laminar flow to the left and a turbulent flow to the right. If you look over here at the laminar flow, you see that what matters is the duct shape, right? You have different lines here for different types of ducts, square ducts, circular ducts, and so forth. What doesn't matter, though, is the relative roughness. You don't see any different lines here for different relative roughness. On the other hand, if you go over here to the left, where you're in turbulent flow, apparently what matters is the relative roughness. These different lines are different relative roughness. And what doesn't matter is the duct shape. You're not seeing any different lines here depending on whether or not the duct is a circular duct or a square duct or anything like that. So the dependence is totally different depending on whether you're a laminar flow or a turbulent flow. And we ought to be able to understand why that's the case just based on our understanding of the behavior and the characteristics of a laminar flow versus a turbulent flow. So here I've sketched the velocity distribution that I would expect for a laminar flow. And you see that you get this gradual velocity gradient that stretches across the entire duct, right? You have a constant molecular viscosity. You don't have any turbulent eddies. You've got the entire duct participating in the velocity gradient. And so it makes some kind of sense then that the shape of the duct is actually going to have a pretty strong effect on what's the friction factor for a laminar flow. Why doesn't the roughness matter for a laminar flow? Well, you can see that the velocity gradient extends pretty much across the entire duct width, and it's going to be kind of a strange looking duct to have roughness elements on the surface that are on the same order as this velocity gradient, right? If we go over here and look at the velocity distribution for a turbulent flow, you can see it's very, very different. The entire velocity gradient pretty much occurs across this incredibly thin viscous sublayer, right? And so it's very easy then to have roughness elements on the wall that are on the same order of magnitude as the viscous sublayer, right? So it's very easy to have a duct where the roughness on the surface actually substantially impacts the velocity gradient and therefore substantially impacts the friction factor. And that's why you see that there's a pretty strong effect of the relative roughness. In fact, if you have roughness elements that are quite a bit larger than the viscous sublayer, so 10 or 12 times the viscous sublayer, you can get out in this region where the Reynolds number doesn't even matter, right? What you're in is this fully rough region where the only thing that matters is the roughness, right? You can see that the friction factor is only a function of the roughness if you're out here somewhere. On the other hand, the shape of the duct doesn't matter at all in the region, is because whether or not you're a square duct or a round duct or whatever shape your duct is, you're going to have the same velocity gradient because the velocity gradient is only dictated by the size of the viscous sublayer. Right? All right, so let's move on to the Nusselt number. Again, we have two different flavors of Nusselt number. We have the local Nusselt number, which is what you would want to get if you were interested in the heat transfer coefficient at one particular location on the duct surface, one particular x value. And you have the average heat transfer coefficient, which is more what you'd want if you wanted a heat transfer coefficient that told you on average what's the heat transfer coefficient over the entire duct length, right? They both have the same basic dependence. So they both depend on, if you look at this, all the same things that the friction factor depends on. The Reynolds number, how long is the duct normalized by the hydraulic diameter, roughness, normalized by the hydraulic diameter, what's the shape of the duct, and then they also depend on two more things. So they depend on the Prandtl number, right, which shouldn't be too surprising, and then they also depend on what is the thermal boundary condition associated with the duct surface. So do you have a duct that has a constant temperature? Do you have a duct that has a constant heat flux, or something else, something between those two things? So if we go back and look at ease, you can see that all this dependence is reflected in the procedural calls to